Hello Calc 3 and welcome back to the last video for the course. This is the second half of section 16.4 and it is fitting that we will be covering one of the most well-known theorems in all of calculus, Green's theorem in the plane. So remember from section 16.3 that we have this interesting notation here to denote the line integral of a vector field f around a simple closed curve C in the counterclockwise direction. So we have our integral sign over C, and then we put a circle with an arrow going in the counterclockwise direction to denote that we're integrating over a simple closed curve. And the first form of Green's theorem says that the line integral of our vector field f around the simple closed curve C is equal to the double integral of the circulation density, or the curl of f in the k direction, over the region enclosed by C. So this is the first form of Green's theorem, and we will state it here. So this is Green's theorem in the circulation curl or tangential form. So let C be a piecewise smooth, simple closed curve that encloses a region R in the plane. So we have a curve, maybe it looks like this, but it's simple and it's closed, and we are going to traverse it in the counterclockwise direction, and the region inside of that simple closed curve will be called R. And this is again all happening in the plane. Then let f equals mi plus nj be some vector field with m and n having continuous partial derivatives in an open region containing R. So maybe that open region would look like this. Just some region containing R on which the component functions have continuous partial derivatives. Then the following is true, and this is Green's theorem here. So the integral of f around the simple closed curve C is equal to the line integral of m dx plus n dy over C. So this is not Green's theorem. This is just restating the original line integral in a different form. But these are both equal to the double integral of partial n with respect to x minus partial m with respect to y, dx dy over the region R. And this is Green's theorem. So the idea here is that we can write the line integral of our vector field around some simple closed curve C as a double integral over the region that's being enclosed by the curve C. And particularly, it's the double integral of this partial n with respect to x minus partial m with respect to y, which you should hopefully recognize from the circulation density that we covered in the last video. So note that Green's theorem says nothing about f being conservative. So in the last section, section 16.3, we found that for conservative vector fields, there are more convenient ways to evaluate line integrals. In particular, we can find a potential function and then evaluate that potential function at the points at the beginning of our curve and at the end of our curve. But Green's theorem applies for many more vector fields than just conservative vector fields. So we don't have that extra condition, which makes Green's theorem more powerful. And often Green's theorem will be easier to apply to finding a line integral than calculating the line integral directly. So now we also have a second form of Green's theorem that states that the outward flux across a simple closed curve C in the plane is equal to the double integral of the divergence of f over the region enclosed by C. So we can again refer back to the same diagram that I've already drawn now. So we have our simple closed curve in green, and it's enclosing some region R in the plane. And the second form of Green's theorem says that the double integral of the divergence of f over this region R will be equal to the line integral over the simple closed curve C of f dot n, which again, hopefully you recognize from section 16.2. So let's state this theorem formally then. This is Green's theorem in the flux divergence or normal form. So if we let C be some piecewise smooth, simple closed curve that encloses a region R in the plane, and we let F equal Mi plus Nj be some vector field where M and N have continuous first partial derivatives in an open region containing R. So again, these are the same preconditions that we had in the first formulation of Green's theorem. Then the following is true. So we have the line integral of f dot n over the simple closed curve C in the counterclockwise direction, and we can rewrite that as the line integral of m dy minus n dx over C in the counterclockwise direction is equal to this expression here. And now we have the double integral of the partial derivative of m with respect to x plus the partial derivative of n with respect to y over the region R that's being enclosed by the simple closed curve C. And again, you should recognize that our integrand here is related to the flux density that we just found in the first half of section 16.4. So we're integrating the flux density over this region R, and when we integrate, we end up with the value for the line integral of f dot n over our simple closed curve C in the counterclockwise direction. And the book does offer a proof of Green's theorem over special regions in the plane, and the proof is given, I think, at the end of section 16.4, but I don't plan on covering the proof just because the proof is long and it would make this video longer than it needs to be. But if you're interested in the proof, feel free to check it out in the book. So now we can move on to our first example, applying Green's theorem. So in this first example, we want to verify both forms of Green's theorem that I presented above for the vector field f of xy is equal to x minus yi plus xj, and the region R that's bounded by the simple closed curve C, which is parametrized by r of t equals cosine ti plus sine tj, where t is ranging from 0 to 2 pi. And notice that this simple closed curve we're talking about is just the unit circle parametrized in the counterclockwise direction inside of the plane, and the region R is just the unit disk inside of that curve C. So to verify the first formulation of Green's theorem, we're first going to evaluate the line integral of f dot t over the curve C using methods from section 16.2, and then we will evaluate the double integral of partial n with respect to x minus partial n with respect to y over the unit disk, and show that these two values are equivalent to one another, therefore just verifying the first formulation of Green's theorem, and then we'll do the same thing for the second formulation of Green's theorem. So first, let's evaluate this line integral of f dot t over the simple closed curve C. First, we need to find f of r of t. So we take our x component and y component of our parameterization of the curve, and we plug it into the vector field f, and we get cosine t minus sine ti plus cosine tj. And then we also need the derivative of r with respect to t, and we'll get a minus sine ti plus a cosine tj. And then the line integral of f dot t over the curve C will be equal to the ordinary integral from 0 to 2 pi of cosine t minus sine ti plus cosine tj, the dot product of that with minus sine ti plus cosine tj. And when we take the dot product, we end up with a minus sine t cosine t plus sine squared t plus cosine squared t. And the sine squared t plus cosine squared t will just give us a 1. So we're left with the integral from 0 to 2 pi of 1 minus sine t cosine t. And when we take an antiderivative of 1 minus sine t cosine t, we get t minus sine squared t over 2. And we evaluate from 0 to 2 pi, and that'll give us 2 pi ultimately. So the value of the line integral is going to be 2 pi. And on the other hand, we want to evaluate the double integral of partial n with respect to x minus partial m with respect to y, and show that the two values coincide with one another. So if we go back up to f as it's given to us, m, the component function m for f is going to be x minus y, and the component function n is just going to be x. But the partial derivative of m with respect to y is then -1, and the partial derivative of n with respect to x is then 1. So the double integral of partial n with respect to x minus partial m with respect to y over the region R is equal to the double integral of just 2 over the region R, which is enclosed by the unit circle, just the unit disk. And 2 is a constant, so we can pull it out of the integral, and we're left with 2 times the double integral of dA over the region R, which is just the area inside the unit circle, or the area of the unit disk. So we're left with 2 times the area inside the unit circle, and then of course the area inside the unit circle is just pi, because area equals pi r squared, and of course the radius of the unit circle is 1. And so we find that the value of this double integral is 2 pi. And fortunately that matches up with the value that we got when calculating the line integral. So this example here should just verify that Green's theorem is in fact true for our particular example. And so ultimately we get that this line integral of f dot t is equal to the double integral of the respective partial derivatives subtracted from one another over our region R enclosed by the simple closed curve C. And from here we also want to verify the second formulation of Green's theorem, which says that this line integral of f dot n over the simple closed curve C in the counterclockwise direction is equal to the double integral of partial m with respect to x plus partial n with respect to y over the unit disk that's being enclosed by the unit circle. So again, we will verify this as well. So notice that we can write f dot n as the line integral of m dy minus n dx over our simple closed curve C. So this is just rewriting the line integral in another form that we already had from section 16.2. And this will equal the ordinary integral from 0 to 2 pi of cosine t minus sine t times cosine t dt. So this is m dy, where we're substituting m with respect to t, and then dy, we're writing that in terms of t as well. And then we want to write n dx in terms of t, and we get this cosine t sine t times dt. And now we can rewrite that as the integral from 0 to 2 pi of cosine squared t dt. So we have a minus sine t cosine t and a plus sine t cosine t that are being canceled with one another, and we're just left with the cosine squared of t. And we evaluate this integral, so we can use the trig identity to substitute and get the integral from 0 to 2 pi of 1 plus cosine of 2t divided by 2. And again, we take an antiderivative of that. We get 1/2 t plus 1/4 times sine of 2t, and we evaluate from 0 to 2 pi, and that'll leave us with just pi. So this line integral ultimately evaluates to pi. And on the other hand, and now if we look at the double integral of the appropriate partial derivatives over the region R, or the unit disk that's being bound or enclosed by the unit circle, the partial derivative of m with respect to x is going to be 1, and the partial derivative of n with respect to y is going to be 0. So remember that m is x minus y, and I think n is just x. So again, the partial derivative of m with respect to x gives us a 1, yeah, and the partial derivative of n with respect to y just gives us a 0. So this reduces to the double integral of just dA over the region R, which is of course just the area of the unit circle, or the area of R, and as we already said before, that's just pi. And so again, we've verified now the second form of Green's theorem, since the evaluation of the line integral of f dot n over c is equal to the double integral of partial n with respect to x plus partial n with respect to y over the region R that's being enclosed by that curve C. So now we can move into the last section for this video, which is to use Green's theorem to evaluate various line integrals, and we'll just go through a couple of examples here. So evaluating line integrals over particularly piecewise smooth curves can be tedious if the curve consists of many smaller curves that are joined end to end, because for each of these smaller curves that are being concatenated together, we have to do a line integral for each of them and then sum them together. But if C is closed and encloses a region R on which Green's theorem is applicable, then using Green's theorem is often easier. So if, for example, our piecewise smooth curve is a square, something like this, and we're traversing it in the counterclockwise direction like this, and we want to find the line integral over that square, instead of taking 4 different line integrals for each of the sides of our square, we can use Green's theorem and just do one double integral over that square. So here's our first example. Let's say we want to evaluate the line integral of xy dy minus y squared dx over the simple closed curve C, where C is a square that's cut from the first quadrant by the lines x equals 1 and y equals 1. So that square probably looks something like this in the first quadrant. And we want to find the line integral of xy dy minus y squared dx over this square now. And we are traversing it in the counterclockwise direction. So we can use Green's theorem. And to do so, we let m equal minus y squared, and we let n equal xy. And now substituting, that'll give us the line integral of n dy plus m dx around our simple closed curve C, or just the square. And using Green's theorem, this will equal the double integral of partial n with respect to x minus partial m with respect to y over the region R that's being enclosed by the boundary of the square. And partial n with respect to x will give us a y, and partial m with respect to y will give us a minus 2y, so we end up with a y plus 2y as the integrand here, which of course just gives us a 3y. And now this ends up just being a double integral problem like we had in chapter 15. So our limits of integration are now 0 to 1 and 0 to 1 because we're just integrating over the square up here. And we take the inner integral with respect to x, and we get a 3y that pops out, and so we're just left with the integral from 0 to 1 of 3y dy, and we get a 3/2 y squared from 0 to 1, which will just give us a 3/2. And so the value for this line integral that we started out with is equal to 3/2. And in this case, we could use Green's theorem to do that instead of taking 4 different line integrals along each of the sides of the square inside of the boundary that we traced out with C here. Okay, now we can move on to the last example of using Green's theorem here. It'll just be another application, but the application is a little bit different. So in this case, we want to calculate the outward flux of a vector field f of xy, which is equal to 2 times e to the xyi plus y cubed j across a square that is bounded by the lines x equals plus or minus 1 and y equals plus or minus 1. So again, I drew a little half-hearted sketch of this over to the right. We're looking at this square in the plane where x is bounded by -1 and 1 and y is bounded by -1 and 1. So we can let C be the boundary of the square and let the square itself be the region R. So all of that area that's bounded by the outside of the square is going to be the region R. And maybe I should label that. So we'll say that this curve on the outside is C, and we will end up traversing it in the counterclockwise direction here when we apply. And the region on the inside is going to be R. So we know from Green's theorem that the line integral of f dot n over the curve C, which is the boundary of our square, is equal to the double integral of partial n with respect to x plus partial n with respect to y over the region R. So this is the second formulation of Green's theorem here in action. And the partial derivative of m with respect to x is just 2 times y times e to the xy, and the partial derivative of n with respect to y is equal to 3y squared. So you can verify both of those partial derivatives for yourself just by looking at the component functions up here. And so now we want to evaluate this, this double integral here, and that'll give us the value of our line integral that's giving us the flux crossing our curve C, which is the boundary of our square. So the double integral of partial n with respect to x plus partial n with respect to y over r can be written as the iterated integral, where we have the integral from -1 to 1 of the integral from -1 to 1 of 2y times e to the xy plus 3y squared dx dy. So I chose to integrate with respect to x first because I think it ends up being easier. And so if we integrate with respect to x first, an antiderivative would be 2 times e to the xy plus 3xy squared, and we evaluate from -1 to 1, and that'll give us 2e to the y plus 3y squared minus 2e to the -y plus 3y squared. And we can simplify a little bit, just combine the 3y squareds together, and we get a 2e to the y minus 2e to the -y plus 6y squared. And now we want to integrate this with respect to y from -1 to 1. And that'll give us a 2e to the y plus 2e to the -y plus 2y cubed. And again, we're still evaluating from -1 to 1. If we plug in a 1, then we get a 2 times e plus 2 divided by e plus 2. And if we plug in a -1, we get a 2 divided by e plus 2 times e minus 2. And these things will cancel with one another, and we're just left with a 4. And so ultimately, we have used Green's theorem here so that instead of calculating 4 different line integrals, one line integral for each of the sides of this square that's showing up in our curve C, we can just evaluate one double integral over the square region R that's being enclosed by C. So hopefully this gives you an appreciation for the power and the efficiency of Green's theorem at some times. Okay, so that is officially the last piece of content for the entire course. I hope you have enjoyed the course up until this point. And the final exam should be posted relatively soon. All of the homework is posted, so you should be set for that. And as always, email me if you have any questions about the content or about any of the upcoming assignments. Just let me know.